And as Ryan said, before we get into kind of multifunction apertures, what they are, what that means for this standards body and for the industry as a whole, I guess I'd preface this with our presentation is mostly about the why. You heard about VITA 100, you heard about 400 gig optics and beyond. There's lots of good reasons, so I'm not saying this is the only reason, but this is one of the reasons that we in the industry really need this type of technology. So look at this sort of as a why use case almost of some of the things that were great presentations yesterday. This is what New Wave does also. So if you look at this presentation, some of these themes we touched on last year, but this year we're going to go deep on specifically multifunction apertures, because if there was anything we talked about last year in the 12 months that came after, this is getting a lot of attention in the industry. So what is a multifunction aperture? Let's start there. Make sure everybody in the room, I'm sure there's some that are like, yep, I've heard about this. I know all about this already, but I want to make sure. If you think about even modern platforms in the DoD's inventory today, surface ships, airborne, rotary wing, fixed wing, all of the above, there is some sensor fusion going on, but in general, the radar has its own antenna structure, let's just call it, and processors. Comms do as well. Electronic warfare does as well. Countermeasures does as well. That is how the industry works today. Even when these systems talk, they pretty much have their own dedicated apertures, antenna structures. It doesn't just have to be RF either. If you think of like EO, IR, and you think of countermeasures versus targeting systems versus pilotage systems, they all tend to be fairly separate as well. Multifunction aperture, when you really just sort of take it down to what are we talking about, we're saying don't look at a sensor front end as being part of any particular application or domain. It is the radar, and it is the comms, and it is the EW, and it is your countermeasures potentially if you think of like receiver exciter and things like jammers. That's what we mean by multifunction aperture. It's software defined. Multiple functions can be deployed simultaneously. You can do dynamic allocation of resources, saying at any given moment, I care mostly or maybe completely about comms, or maybe I compare and contrast that with I right now care all about the radar or something in that way. And Ryan's going to get into those trade-offs in a second and what that means. But at a high level, when you imagine that world of front end being very wideband, whether it's optical, IR, or RF, and then really centralizing processors, you can see where big optical pipes and very high-end compute is going to come into play. And that's why I sort of introed this as when you think of 400 gig optics and beyond, and you think of VITA 100, this is why, or one reason why. So on the board right now, there's a 5th gen suite. This is the F-35. It's a publicly available graphic that anybody can go get. But I want to highlight sort of even the F-35, even a Gen 5 fighter, and this is not unique to fighters. You could look at your rotary wing out there. You could look at your surface fleet right now. It looks similar in the sense that you have a domain-specific set of apertures and domain-specific set of processors by and large. And on this graph, you can see radar, you can see your forward-facing, radar warning receivers. There's EW systems on there. There's countermeasure systems on there. They all have, to some degree, their own federated apertures and federated, separated processors. And then there is sensor fusion going on there too. I don't want to make it sound like there's not. There is, but by the time you're fusing a lot of that data, quite a bit of pre-processing has been done, and it's domain specific. The cons of that are, these are swap constrained platforms, right? If you are going to allocate space, weight, power, thermal to domain specific things, you've taken it away from being able to use it in other domains at a given moment in time. Think about like dynamic capabilities there. So as I hand this off, I guess my last message here would be, even in the stuff out there today, you don't have what's coming. And in the MFAs of Gen 6 on the airborne side, but this isn't going to impact all the other vehicle platforms as well. So embedded, deployed platforms. we're going to see MFAs come on, and it's going to drive a huge need for the technologies we've been talking about here. So with that, I'm going to hand this over to Ryan.
So here's a rendering of what a next-gen multifunction aperture would look like. And you can see here the blue dots are phased array antennas, the yellow dots are electro-optical. But what's unique here, rather than having these sensors dedicated for the specific purpose of comms or EW or radar, you look at those phased array antennas, you use one antenna that's it's really high performance, can handle a wide spectrum, and you put multiples of those all over the platform, and you give access to all of that data to your the processing resources. So you can see as this starts to build up, the significant challenge here is data movement. Just one of these phased array antennas, if you start thinking about it, say it has 64 elements. You have I and Q data. You're sampling at 100 gigabits a second. 14-bit sample depth. You can see how it's really easy to get to the point where you have hundreds of terabits a second of data. Even if you down convert that by a factor of 256, you can have 700 gigabits a second of data per sensor, and you might have 16 of these on a single platform. So the sheer amount of data is extremely difficult to deal with, and you need to get all of that into the processing resources. So all the things that we were talking about yesterday with the optical transceivers, really that is the solution. You need optical connections from the sensors into the central processing regions. And we've talked a little bit about it before, but the ability on the sensor side to efficiently digitize that data, do some small amount of processing on it, and then convert that over to optical is really important. One technology that we really track in the industry is what's happening with integrated photonics. That's still in a research phase, but we've seen demos of that with the Intel chipset in the last year. We've seen a demo of those with an AMD FPGA the year prior to that, so it's still in a research phase. But we think the ability to integrate some of those things on the chip, also integrate WDM, wave division multiplexing, get multiple wavelengths on a single fiber. Those are all things that are going to need to happen to get the most out of this architecture. The final thing on here, we talk a lot about the Ethernet and the big pipes and moving the data from one place to another, but there's another important aspect to that, and that's the efficient protocols that are riding on top of those Ethernet channels. Just because you can move all that data from one place to the other, you don't want to overwhelm the processor subsystems with it. So something like Rocky V2, is all set up to really move big chunks of data efficiently from one place to another, get that into the host memory for the processors, and enable them to actually to work on that data. CXL is another standard that is getting adopted in the data center world as well, and would work very well in an architecture like this. On the actual processing side, there are some unique challenges as well. When you're creating this dynamic environment where you can run multiple missions and do lots of different things with this hardware, you need to design a really flexible hardware system, and oftentimes you're designing it for algorithms you don't know are going to be used, or there's future algorithms that need to be supported you don't know that they exist. So you have to be really thoughtful about the system that's put together, and we like to think of this as you try to get a lot of heterogeneous computing elements available so they can be used, and you can use the most efficient one at any given time when you need it. So here you see a couple of compute-intensive payload slots, and we just have a FPGA and a CPU and a GPU showing that you get that nice flexible heterogeneous computing environment that can be stamped out multiple times depending on the size of the platform. So we think that this is using the VITA standards is an easy way to put the system together and provide the ability to make use of all this sensor data that's coming into the system. Vita 100, we talked a lot about yesterday about the connectors enabling, the highest speeds available on the interfaces, enabling the latest and greatest silicon technologies. All of those things are very important in this next generation MFA architecture. Added benefit, to using the standards and the MOSA approach is that we should be able to upgrade these systems at a more rapid pace, get the latest and greatest silicon in there and not wait 10 years or 5 years, but hopefully shrink that cycle down. The last item on here that we think is really important and neat is that this whole architecture does allow a whole set of new businesses to participate in the rapid innovation. Not just the extremely, before with the stovepiped sensor processor architectures, it was, you had to be able to make a really high-end sensor and do the compute and write the algorithms. Now you can go get the really high-end sensor from one company, you can go get the compute from a number of different companies, and you have a whole set of people that can work on the algorithms and come up with really neat and cool applications that can run on the hardware and make use of all this data. So this whole ecosystem is now set up, allowing lots of people to participate in it, which we are excited about. The last piece here is there are a number of challenges that lie ahead. All these things look great in concept, and there's, to really take advantage of what this architecture can provide, there's some things that need to be figured out. System qualification is a big thing. As we try to shrink down that cycle of upgrades and adding new algorithms, we need a way to qualify that. Right now, it takes a lot of time and money to qualify a system to be used, on an airborne platform. Some of the work that's being done in model-based systems engineering, specifically, moving to digital twins and creating a really robust emulation environment that has, not only the platform in it, but all of the things that it's going to encounter in its environment. So you can test all these new algorithms and start to get down to a pace where you can update things every month or week or on a day-to-day basis is going to be really important. Next piece is, how do you allocate all these resources? Yesterday Dan talked a little bit about system management and how important that is going to be. If you want to allocate a number of resources for one mission and set priorities over another mission, you need a way to do that, and that's going to be a challenge to solve in the future. We talked a little bit about all the cutting edge chips, how large they are, how much power they create, how much power they need, all the increased pin counts. So that's where all the things that we're talking about in Vita 100 are going to come into play. And then finally, more and more capability is desired in smaller and smaller spaces. So the work that's being done in Vita 93, the QMC that we talked about yesterday, VNX Plus, some of the working groups looking at even smaller form factors is going to be important as well. So we really appreciate all the work that everyone's doing in developing these standards, and we're excited about what they're going to enable in the future. So with that, we'll take any questions that anyone has.